Hello everyone, I'm Qianyue from Tsinghua University. Now I'm very glad to introduce our work on understanding the urban pandemic spreading of COVID-19 with real-world mobility data. With the sudden outbreak, the COVID-19 pandemic has been sweeping the globe with a rapidly growing number of infected cases. By the day I made this video, there are more than 50 million people infected by it, and even more people are involved into the fight against this invisible enemy. At this very moment, it is of high significance to understand the spreading patterns of COVID-19, and thus we can fight against it. We know that a lot of people live in big cities, and it can be very easy for the pandemic to spread around very quickly due to the dense population in cities. However, recent studies mainly focus on evaluating its high-level spreading and few is known about the spreading process of COVID-19 in the urban environment. For this reason, we focus our work on building an epidemic simulator on the level of within cities. And further, we conduct experiments based on the simulator in downtown Beijing and uncover the spreading process of COVID-19 in the urban environment. There exist several challenges in building the simulator. The first one is to choose an appropriate spatial-temporal resolution to capture the mobility of large-scale urban population. We know that Beijing is a large city with a total population size of more than 20 million. And in our starting area, downtown Beijing, the population size is about 11 million. There is a choice to build an individual-based model, which is to simulate the behavior of every single person and thus simulate the pandemic spreading process. This method can achieve a quite precise result, but there are some shortcomings. Firstly, it is computationally expensive. Simulating on such large population size in the real world will take up quite a lot of hardware resource and consume a long time. It is also difficult to collect adequate data describing the behavior of every single person precisely. For this reason, we design a block-based model instead of the individual-based one. We divided Beijing into 675 blocks according to the main road network. We regard people in each block as a subpopulation group. People in each block interact with each other, and people in different blocks also have interactions through population mobility. And for temporal resolution, we set the steps in simulation to be 30 minutes, which will draw a simulation result in high precision. The second challenge comes in incorporating urban-level mobility data into the epidemic model. Our real-world mobility data are gained by collecting GPS coordinates for users accessing local-based internet services. It offers fine-grained description of intra-city population mobility over 3 weeks. The dataset consists of two parts. One is the number of internet service users who travel from the S block to the J's during the T's time step, which is denoted as MIJ. The second part is the number of internet service users in the S block at the start of T's time step. We denoted it as NI. An average is calculated over the 3 weeks, and thus we get a description of the behavior of such internet service users in 1 week. They are denoted as big MIJ and big NI. Based on big MIJ and big NI, we can calculate the total population size in the S block, denoted as big NI with square brackets. We also calculate the possibility for people in the S block to travel to the J's at the T's time step, denoted as PIJ. Detailed process can be found in our paper. When using lines to visualize PIJs, we can get these two pictures, and the red line indicates busier population flow. The left one is PIJs at 8 a.m. Monday morning, and the right one is at 6 p.m. Friday afternoon. It is obvious that the strength of population mobility varies from morning to evening and from workday to weekend. By incorporating the population mobility information into our simulation, we can draw a more precise result on the pandemic spreading process in the urban environment. There is also a challenge in simulating the special epidemiological characteristics of COVID-19. Firstly, we collect and apply parameters from medical researchers, describing the feature of COVID-19 precisely. Secondly, we know that in the spreading process of COVID-19, there exists a group of special people. They are infected but are asymptomatic at the same time. It is one of the features that distinguish this pandemic from others. We take infected asymptomatic cases into consideration and thus able to grab the virtual feature of COVID-19. Now, let's see the whole simulation process. We consider 6 states susceptible for people who have not been infected and may be infected in the future. Infected people, recovered people, and latent people in the incubation period. They are infective. Infected asymptomatic people as mentioned above, and finally people who unfortunately passed away. At the beginning, we initialize the number of people in different states, in different blocks. It is denoted as XJM. We can see there are blocks and each block has a population size. Some people are initially infected. Some are initially in the incubation period. Then we simulate the state transition in each block. Transition number from state M to N in block J is denoted as FJMN. The values of FJMN are given by a polynomial possibility distribution with parameters of population size in a certain block and the transition possibility between different states. Sum of the transition number to state M and minus those from state M. We can get the variation of XJM and use it to update XJM. We can see in state transition simulation, some health people are infected by the infected cases, and some are infected by cases in the incubation period. They are infected and turn into the incubation period. Some people who are previously in the incubation period may turn into the I state, and some may turn into and be an infected asymptomatic case. Some people in I state may unfortunately pass away. Some infected or infected asymptomatic people recover. Then we deal with population mobility between blocks. The number of state M traveling from block I to J is denoted as TIJM. The value of TIJM are given by a polynomial possibility distribution with parameters of population size in a certain block and the possibility for people to travel from a block to another. Sum of the number of people who travel to a block and minus those who travel from it. We can get the variation of XJM and use it to update XJM. We see people in various states may travel to different blocks. By repeating the above steps, we can go down along the simulation process, and after a certain period of time, there are no more people being infected or in incubation period, apart from those who unfortunately died, or people are not infected or have been recovered. Then the pandemic spreading process comes to an end and we can get the final result. By applying this simulation process and combine it with some programming skills, we can simulate the pandemic spreading process in downtown Beijing very efficiently. It only takes about 8 seconds to cover 1 day in the real world, only on a normal laptop. Now, we conduct experiments on the pandemic spreading process based on the built simulator. In the real world, mobility control or travel restriction is a common way to intervene the pandemic spreading process, and thus we evaluate the effect of different mobility control policies. Before the experiment, we defined 3 metrics in order to measure the pandemic spreading process quantitatively. The first one is infect rate. It measures the percentage of infected cases at a certain time. We calculate it by summing up the number of infected cases and divided it by the total population size in downtown Beijing. The second one is peak date, which is the time when infected rate reached the top during the whole process of pandemic spreading. And the last one is peak height, which means the highest level of infected rate during the whole process of pandemic. The experiment settings are as follows. We assume that there are 15 initially infected cases and the outbreak spot is set to be block number 0. A simulation lasts 500 days is conducted, covering the whole process of pandemic spreading. In this experiment, we design and test 3 mobility control policies. We call the first one simple ratio mobility control between blocks, where the traffic flows between different blocks in the whole city are restricted by a restriction rate, gamma. Gamma is a positive number no larger than 1. Results by our simulator are shown in the graph. We note that the baseline, the blue line, and the orange line almost overlap each other. The green and red line shows a relatively obvious decrease on peak height and a delay on peak date. Quantitative calculations indicate the same results. That is to say, only when gamma is very small, maybe no larger than 0.1%. In other words, the restriction is very strict. It will make a difference. It is not good news for such strict mobility restriction. It is almost impossible to be realized in the real world. And even if it is realized, it will cause a huge influence on people's daily normal life and the social economy. Thus, we can say that the simple ratio mobility control between blocks is not a good enough policy. As an improvement of the simple ratio mobility control between blocks, we put forward dynamic mobility control between blocks. There are 2 parameters in this policy. One is the control threshold, denoted as CT, and the other is the adjusting frequency, CF. The executing process of this policy consists 2 steps. Firstly, we perform a judgment after every period of time lasting CF. Then we ban all traffic flows from or to blocks with number of infected cases larger than CT until the next judgment. We choose 3 different control thresholds and 3 different adjusting frequencies, combine them with each other, and we get 9 results. When compare different adjusting frequency between the 3 graphs, we can have the conclusion that there is not a very obvious difference and the clusters of curves are similar. When compare results with different thresholds, that is to compare the curves in a single picture, we found that a smaller control threshold leads to an obvious decrease on the peak height and a delay on peak date. The result of quantitative calculations can be found in our paper, and it shows the same conclusion. This means when the control threshold is set to be a relatively small number, we don't need a very small control frequency, or we don't need to adjust the banning on mobility very frequently. This ensures the dynamic mobility control between blocks is relatively easy to be applied in the real world. We also evaluate the influence this policy caused on daily traffic, and the control threshold is set to be 2. I mentioned in the first policy, when about 99.99% or more population flow is restricted, there is a relatively obvious difference. But the dynamic mobility control shows a lower influence on daily traffic flows, and the influence goes down with the pandemic fading away. This also indicates the policy is much cleverer than the simple ratio one. Here comes the third policy. The first 2 policies both focus on population mobility control between different blocks, and so we put forward this mobility control within block policy, in which traffic flows within every block are restricted. as this obviously decreases the chance people contact with each other, and thus it leads to a reduction factor gamma 0 on the infectivity. The result of simulations under this policy are shown in the graph, and we notice that all the curves shows an obvious decrease on peak height and delay on peak date. The quantitative calculations also indicates a more than 10% difference if gamma 0 is 19%, a very close to 1 number. This means that not very strict restriction can lead to an obvious effect. That is to say, it is a smart policy that not only intervenes the pandemic spreading effectively, but also causes a limited influence on people's daily normal life and the social economy. After studying the effect of different mobility control policies, we conduct extensive experiments and try to uncover the relation between features of pandemic spreading process and the population distribution and population mobility in the city. The metric of population density indicates the population size on a unit area, given by a ratio of population size and the area of block. The metric of population mobility is a measure how busy the population mobility related to a certain block. We also define one more metric to measure the pandemic spreading. It is accumulated infection rate, which is the percentage of people previously or currently infected at time t. In this experiment, the number of initially infected cases is still set to be 15. We apply a normalization on the population density and population mobility of all the blocks, and the result is shown in the left graph. We can find both population density and population mobility vary from low to high. We choose 13 different blocks with both low and high population density and mobility. We take them as outbreak spot one by one. Thus, they can have a good representation of blocks with different population density and mobility. This way, we can eliminate the influence on the result caused by different outbreak spots. The lasting time of simulation is 1 year, and we conduct 5 repeat simulations in order to get rid of the stochastic factors and get a more credible result. Here, we apply curve fitting method to measure the features of the pandemic spreading process in a more mathematical way. The curve of infection rate in each block is fitted using a Gaussian-like function. Due to the attributions of Gaussian-like function, the value of m is equivalent to peak height, the value of mu is equivalent to peak date, and the value of sigma indicates the length of pandemic duration. The curve of accumulated infection rate in each block is fitted using an exponential function, where the value of a indicates how rapidly the pandemic spreads. In all the curve fittings, the value of r squared is larger than 0.99, indicating a very good fitting result. Generally speaking, the values of m, mu, sigma, and a all vary with different population density and mobility. For example, the value of m increases obviously as population mobility goes up. This indicates blocks with high population mobility meet a higher infection rate peak, which especially alarms us that the medical system in high mobility blocks are highly risky to suffer from heavy pressure. And thus, more effective control policies and more adequate preparations are called for. More detailed results can be found in our paper. We find that population mobility have a much obvious effect on the spreading process of the pandemic than population density does. This sheds light on the key role that population mobility plays in the process of pandemic spreading. This also provides an evidence for the necessity of intervening pandemics through mobility control. So, in summary, in this paper, we incorporate real-world mobility data into the epidemic model of COVID-19 and build an efficient simulator on block level. After studying the influence brought by various mobility control policies under different implementation strengths, we conclude that mobility control within blocks is the most effective one, which offers a meaningful suggestion for the real-world pandemic intervention. We further studied the difference of pandemic spreading due to various population density and population mobility levels. Our study not only sheds light on the key role of mobility control policies, but can also be very meaningful for making targeted policies to fight the pandemic in different blocks. Our simulator is available on GitHub, and I believe based on it, more intelligent policies and more fundamental spreading phenomena can be uncovered. Please see more details in our paper, and thanks for your listening.